Hello and welcome to this video. In today's video we will study some applications of divisibility test, and the theory of divisibility test we have studied in the last video, and also we have solved few exercises in the last video. Let's start with the first question. Find the missing digit of the number, and number is this one, 95555, and the box is in place of missing digit 4353, so that the given number is divisible by 11. Okay, suppose the missing digit is x, then we have 9 tetra 5 x 4353 is divisible by 11, and we know that by divisibility test 11 divides an integer n if and only if 11 divides summation I is equal to 0 to m minus 1 to raise power I ai, if n is equal to am 10 to raise power m plus so on a1 10 plus a naught. Alright, now we see that the given number is this one, so this can be written as minus 1 to raise power 0 into 3 plus minus 1 to raise power 1 into 5 plus minus 1 square 3 plus next minus 1 to raise power 3, which is minus 1, 4 plus next is 1 into x minus 1 into 5, 1 into 5 minus 1 into 5, then 1 into 5, and then minus 1 into 9. Alright, and this will be, after simple calculation, x minus 12, and this means 11 divides x minus 12, and hence 11 divides x minus 1. This means x minus 1 is equal to actually 0, because x minus 1 must be less or equal to 10, and anything which is less than 10 and is divisible by 11 is actually 0, and this means x is equal to 1. So missing digit is 1. Alright, we move to the next question. The statement is, for any number x, if y is the number obtained by reversing the order of digits of x, and if x is divisible by 9, then show that x minus y is divisible by 9, or 9 divides x minus y. Alright, let x is equal to am minus 1 up to so on a1 a naught. This means because x is divisible by 9, so 9 divides a naught plus a1 plus so on a m, and the y is obtained by reversing the digits. So this is a naught a1 up to so on a m minus 1 a m, and we know that a large number is divisible by 9 if the sum of its digits is divisible by 9, and we clearly know that 9 divides am minus 1 plus so on plus a1 plus a naught by this given fact. Now consider, if we see x minus y will be, of course, am minus a naught, because the digit at the mth place of x, we will subtract the digit of the mth place of y from that. And similarly, the next one will be am minus 1 minus a1 plus so on. Sorry, it will be not plus, and so on. It will be a1 minus a m minus 1 into a naught minus am. Now we obtained a new integer which is x minus y, and these are the digits for the new integer. Alright. Now by divisibility test, this integer will be divisible by 9 if the sum of its digits will be divisible by 9. So we check. 9 divides am minus a naught plus am minus 1 minus a1 plus so on a1 minus am minus 1 plus a naught minus am. If we see, every ai is appearing two times, once with positive sign and once with negative sign, and this means 9 divides 0. And so the sum of the digits of this integer is divisible by 9. Then by divisibility test, this integer is also divisible by 9, and that is what we want to prove. We move further. Question number 3. Alright. The statement is, prove that p divides p is a prime number other than 2 and 5, infinite many integers of the type 9, 99, 999 and so on, and 1, 11, 111 and so on. The statement shows that it is not necessary that every integer of this type is divisible by p, or every integer of this type is divisible by t, but infinite many integers of this type will be divisible by p. Alright. Not all, but infinite many. Now since the integer of this type can be written as a to raised power k minus 1 if these 9 are k times. Alright. Now let p be a prime number different from 2 and 5. Alright. Let an integer L is equal to m into p minus 1. Now we take this L to the 10 to the power L, and of course we know that the value of L is equal to m into p minus 1. So m into p minus 1, and that can be written as 10 to raise power p minus 1 into m, and that is congruent to 1 mod p. This is Fermat's theorem, which we will study, Fermat-Little theorem, which we will study in the coming videos. Alright. Now, and this 1 to raise power m is also congruent to 1 mod p, and this means 10 to raise power L minus 1 is congruent to 0 mod p, and hence p divides 10 to raise power L minus 1. L is an integer. So this shows that p divides infinite many integers of type 9, 99, 999 up to so on. For if we change the value of m, we will get different integers of this type, and so we can replace infinite many values of m, so we get that p divides infinite many integers of this type. Now since 1 1 up to so on 1 1 can be written as 10 to raise power k minus 1 over 9, and of course 3 divides 10 to raise power k minus 1, because this is divisible by 9, so it is divisible by 3 for all k, and this means 3 divides 1 1 up to so on 1 for all m greater than or equal to 1, and these 1 1 1 are m times. So that's all about this video. See you next time.